All right, now the last topic of section 2.8. All right, if you're randomly given a matrix, how do you find the basis for the column space? Let's recall, if matrices A and B are equivalent via elementary row operations, then AX equal to 0 and BX equal to 0 have the same solution sets. We have done that before. We have given a matrix A reduced into a B such that as like a reduced echelon form, and then we can figure out the answer for that. So if matrix A and B are equivalent via elementary row operations, then they have the same linear dependence relationships as one another. So this is the case if this is saying if, all right, x1, x2 to x sub n is a solution to both ax equal to 0 because a and b are equivalent, so they have the same solutions, then that's the same as saying x1, a1 plus x2, a2, xn, a sub n equal to 0. And so this is true. x1, b1 plus x2, b2 to x sub n, b sub n equal to 0. So the same axis here work for both systems. So the linear dependency of A's, the columns here, the vectors here, and linear dependency of B's, the columns here, are the same. So what good does that do for us? Well, here's a look at an example here. Okay, let's look at example 8. Here we have a matrix right hand side A, so have A1, A2, A3, A4, A5 is column vectors, is equivalent to the matrix B, which is the reduced echelon form on the right. Recall this right hand side B is the same we have on the previous example right here, the same B right here, if you recall, that's the same B. So here, they are equivalent via elementary row operation, meaning the right hand side B is a row reduced echelon form of A. Okay, so we want to verify, or we know that in B, the columns of B, which did that a while ago, B3 equals to negative 3B1 plus 2B2. So we know B3 equals to negative 3B1 plus 2B2. Okay, that's same dependency. We can say we want to verify for A. Does that work for A? Whether this is true. A3 equal to negative 3A1 plus 2A2. Is that true? Okay, let's try. So negative 3A1 plus 2A2 equals to negative 3 times the first column, which is, we can see, 1, negative 2, 2, and 3, plus 2A2, which is 3, negative 2, 3, and 4. Okay, add these two together. At the top we have negative 3 plus 6, and we'll have 6 minus 4 minus 6 plus 6, and then minus 9 plus 8, which we obtain 6, 2, 0, and negative 1. Okay. All right, so you can see that this is exactly, not 3, it's 3, my bad. Okay. All right, you can see that is A3. Okay, so we can use a linear, obviously you can see that it's easier to find out how is B3 depends on A1, A2 than from A3 depends on A1, A2. If you look at the reduced echelon form, it's easier to figure out the linear combination of that. All right, so you can also verify that A4 equals to 5A1 minus A2 because we just showed that a while ago. B4 equal to 5B1 minus B2. You can verify on your own. So, to find the basis for any matrix space, let's say, well, let's don't do that. Draw, erased it. Column A. How do we find the basis of column A? Well, find all pivot column of A. Okay, so to find pivot column of A, we'll first find the reduced epsilon form, and then find the corresponding number of columns, and go back to the original one. So in these questions, all right, we know the pivot column is column 1, 2, and 5. Therefore, your basis for the column space A will be A1, A2, and A5. All right, so I have a last theorem here, the theorem 13. It says the pivot columns of a matrix A form a basis of the column space. A, which is called a column space A. One last thing to remind you, something I just said a while ago. The basis of column space A and null space of A contains all columns of A. And they are complement to each other. What does that mean? Here we have A1, A2, A5 as a basis of column space. If you recall, the null space for B is B3, B4, B3 and B4. Therefore, A3, A4 will be the basis for the null space for A as well.